This is deep learning. Today we're going to talk about models of deep neural networks. Neural network models combine modules to provide higher and higher performance on a large dataset, for example, ImageNet. Over the years, they have become larger and larger, helped more and more by powerful CPUs and GPUs. Recently, more emphasis on keeping the computation limited has arisen due to the deployments in data center, which have always limited resources. The future winners are always going to be the network models that have more accuracy per flop, and not just accuracy. So these are some guidelines about the model design. So these are, we'll start describing some of the models from the simplest to the most complex and the most recent neural network that have won also the ImageNet competition. So the ImageNet competition is one of the largest measure by which these networks are evaluated, as you will see soon. So the first model that we will see is a convolutional neural network model, and it's the LeNets 5 model, which you can see from the publication given in this diagram. So what it does is it has an input of 32 by 32, and then there are 6 convolution of 5 by 5. And then there's a subsampling by 2. There's another convolution of this 6 map into 16 maps with another 5 by 5 kernel. And there's another subsampling by 2. And there's a final convolution from the 16 to 120 single unit. And then there's 1 and 2 layers of multi-layer perceptron. This is how the model looks in Torch 7. So it's actually quite nice and compact. You can create a model as a sequential unit, and then you can add modules to it. In this case, we can add the spatial convolution from one image, so this is only one color image, or black and white, for example, into 6 maps of 5 by 5. After the convolution, we apply hyperbolic tangent nonlinearity, or any other nonlinearity you would like, to all the output maps. And then there's a spatial max pooling that will basically take 2 by 2 regions of the image and find the maximum and report that value. Then we have another layer of spatial convolution. Actually, this is supposed to be from 6 to 16, because 6 is the output here, same as before. And then from 16 we have a final spatial convolution of 16 to 120. We have a linear layer, an hyperbolic tangent, and another linear layer. So this is like the last multi-layer perceptron. This was a very popular, one of the first deep neural network trained all with backpropagation. It was in the mid-90s, and so it's a fairly small network because of the small computational capabilities that we had at the time. One of the big revolution in classification came in 2011 with the model AlexNet. In this case, we call it one-word trick. The link is provided here. There are multiple versions of this AlexNet that came about. We'll describe the OWT, or one-word trick model that came maybe the year after. I think it's the year 2012. So this is the model in Torch again. Here we divided the model into features and classifiers, so don't mind that. Imagine it's model everywhere. So this takes a much bigger image. It's a 220 by 224 by 224 image. So the ImageNet competition image size is 256 by 256. There's a spatial convolution, so this is an RGB image with 64 convolved into 64 maps of 11 by 11, and there's a stride as well. There's a batch normalization for training, you can ignore that for now. A ReLU nonlinearity, rectified linear unit nonlinearity, and then a max pooling with 3 by 3 with overlap of 1, so with the stride of 2 by 2. And this is the size that each operation will give you. So from 224, the size goes down to 55. After the max pooling, from 55, you go down to 27. There's a second layer of spatial convolutions from 64 to 192. This time is a 5 by 5 kernel. And we try to keep the same, we padded the image so that it has the same size. Again, a ReLU, a max pooling again with overlap. So after the max pooling, this number is divided by 2 basically. Then another spatial convolution, again padded. So this time it's a 3 by 3 from 192 features to 384 features. So now lots of features fully connected. A ReLU, another spatial convolution of 3 by 3 from 384 to 256. So now we're going down a little bit. Again, it's 13 by 13, the image. ReLU, another spatial convolution, 256 to 256 with 3 by 3, same size. Finally, we have a ReLU and a max pooling again of 3 by 3 with a stride of 2. Now the image becomes 6 by 6. We then resize this vector 6 by 6 into 36, 256 by 6 by 6 values. Dropout, you can ignore it, now is another training technique. We have a linear layer to 4096, and then we have another linear layer and an output. So this is what the AlexNet one-way trick network is all about. After that, a year or two after that, came the VGG-A model. So these were multiple neural network, or more and more complex. The interesting thing is they had most of them used convolution of 3 by 3. So this is how the model would look in Torch. So this is the VGG-A, for example. So the configuration files will say how much features we have when we have a max pooling or not. So you start with image of 3 by 3 to 256 by 256, 224 by 224, sorry. And then what you do is you have, you add, for all this configuration file, you had basically, initially, if it's an M, you do max pooling. Otherwise, like in the first case, it's a 64. Now we do 3 into 64, all 3 by 3. And then there's a, you had this convolution, and you do a nonlinearity. Then you do this again. Now with M, so you do max pooling of 2 by 2. Then it's 128. So now you go from 64 to 128, again 3 by 3. Then there's another max pooling. Then there's 256 to 256 layers, and so forth. And after that, basically, you end up with a 7 by 7. You create a single vector 512 7 by 7. And then you do linear combination to 4096 unit. Again, you do threshold, which is similar to ReLU, rectified linear unit. Another linear layer, 4096, and then another threshold nonlinearity, and then another linear layer to the number of classes. For example, could be 1000 in ImageNet. So now you can see how this is a quite complex and long neural network, how it can be described just by a few lines in the Torch, and that's why we really love this tool. After that, we want to describe the model of GoogleNet. So GoogleNet is a more complicated module, so that you can see here in the figure. It has and the previous layer comes in from the bottom, and then there's multiple parallel paths basically that are concatenated together. So you basically extract features different kinds, one with 1x1 convolution, first with 1x1 convolution, then 3x3, then 1x1 and 5x5, and then there's one that does max pooling and 1x1 convolution. These 1x1 convolution are used to reduce the number of filters. So then all of these different modules are concatenated together, and this is called the inception module. And so here you see how this is done. Basically, it's similar to other network, 3 input of 224 by 224 or similar value into 3 to 64 convolution with a 7x7 kernel. A stride of 2. Then there's a max pooling. Then there's another special convolution, 64 into 64. ReLU, another special convolution, 64 into 198, another ReLU, then a max pooling. Now you had inception modules, and so these inception modules are described here. How many features are going in, and then basically how many 1x1 convolution, how many 3x3 convolution, how many 5x5 convolution, and then what is the pooling average in this case, and what is the feature at the output. So you have 192 features coming in, and then you have 64 plus 64 plus 96 plus 32 features at the output. So this is repeated a few times. There's a special convolution, then there's more inception modules, and eventually more inception module. And notice here we're basically missing the classifier. At the end we do an average pooling over the 7x7 that we do, and then there's just a linear layer to classify. So when we eliminated this big classifier, and GoogleNet is quite efficient to do that, but it became quite a more complex network. Here you can see how you can design the inception module and how it's done. So this is the inception function that basically produces this kind of architecture in Torch as well. Feel free to browse it at your own will. The latest model that was one of the most efficient and most effective is the ResNet model, or residual network from Microsoft. So this network actually, if you can look at VGG, is actually a very deep network where all the layers are about 3x3, but they also introduce between two modules, they introduce like a skip connection. So not only you go through this layer, but you also pass the input to the next couple of layers. So this gives a lot of power to the network, because it can decide whether he wants to extract features here, or he wants to send the whole image and have it extract more features at another point. So it looks like this model gives a combination basically of depth but also parallelism because of this skip connection. What is usually done for this model is we use the bottleneck function, which implements basically this kind of operation. You go in with some number of features, like 256 for example. There's a 1x1 convolution that takes the 256 and reduce them to 64 in order to save computation. And then there's a convolution 3x3, again with a smaller number of features. Then again another 1x1 that basically brings back the same dimension as before. And then you not only you go do this, but you also concatenate the output back. So this is what we just described as in Torch. So a convolution of 1x1, ReLU, convolution of 3x3, and then convolution of 1x1. And then you can basically create different kind of ResNet, 18, 34, 50, 101, or 152 layer. This is like the one that won just last year, the end of last year, the ImageNet competition. And then it's actually quite simple to create the ImageNet model. Is very simple. This one has only convolution 3 to 64, a ReLU, a max pooling with overlapping, and then it has this this layer of bottleneck. Okay, so bottleneck defined as this or as this. So if you take the 152, basically you take the bottleneck function that we just seen, and you do it 3 times, in this block, 8 times in this other block, 36 times in this other block with 256, and then 3 times F512. Then you have an average pooling classifier, basically. There are lots of other models that are important, like overfit, networking network, inception v3, v4, and SqueezeNet, which squeezes a lot of computation. And there's some coming up basically every month. In this blog report, you can see also more information about what we just described and a link to all the papers. I highly recommend you to read each one of these papers, study the architecture, discuss it with your peers and colleagues in order to really understand the evolution of this neural network, their capabilities, what they can do, and what they'll be able to still do. I also encourage you to keep an eye on the recent literature by signing up to Google groups, for example, or Google Plus groups, other Facebook and Twitter groups that basically list all the papers. And keep an eye on, or have Google alerts that keep an eye on the latest and greatest network coming out from research.